Hello everyone, this is Gregory from ChemCore. This video we're going to be doing the resonance worksheet. If you haven't had a chance to look at this worksheet, it's in the description below. And if you haven't watched my topic video on resonance, also should be in the description below. I also suggest just to look at the answer key, check what you got right, and you can skip forward to whatever question you need because some questions you may have already figured out. In the first question, we're trying to write the resonance structure that results from this movement of electrons. And this is what usually these electrons would look like. We'll have these arrows kind of showing from the source of the bond to the destination of the bond. Now the first step is to include these type of arrows. In resonance structures, we kind of show double-sided arrows to show that they both exist at the same time. Let's start from the bottom left corner. Okay, so we're going to have our little nitrogen. And we form a double bond there, clearly from this arrow. And then since we know none of these bonds are actually going to break, none of these single bonds, let's just go ahead and draw that cyclohexane. Because I know the general structure of the cyclohexane is still going to be there. I realize that this double bond is going to move up. All right. And then this double bond is going to move on to the right. So we're going to move that double bond to the right, form that double bond. From here, the double bond that holds that oxygen is going to move up into what is clearly a lone pair. Clearly a lone pair. And so we're going to show an extra lone pair. And then we're going to finish off with that bond. Now what's interesting is that this oxygen will have a negative formal charge. It has one less bond than what it likes. But this nitrogen will have a positive formal charge, right? A +1 formal charge. Because it has an extra bond, right? It has 4 bonds here. Nitrogen likes 3 bonds. And so if you look at the original structure, you can note that the net charge, or I'll just write NC, is actually 0. And on the right side, that's a straight mark, and on the right side, we also have a net charge of 0. Still 0. That's pretty interesting. Will this be stable? I mean, definitely less stable than our original. We have charges here. You know, we usually don't want charges. But it's not possible, right? It's still valid, right? Our total charge is still 0. In the next question, we're kind of doing the opposite. We're given two resonance structures, and we kind of have to show curved arrows that would convert A into B. Now, the important part is that we're converting A into B, and so we're only showing the arrows on the A. We're not really showing arrows on the B going backwards. That's a common misconception I remember making as a student. Just look at what they're asking you. That's the side that actually became a resonance structure. And so what I noticed first is all the way in the bottom is that this nitrogen loses its lone pair, and we get a bond up here. The only way to really do that is to move this lone pair up into a double bond. Now the other thing that I noticed is that this double bond just flipped over onto the other side. And we can do that just by moving this double bond over here. Now something else is that this double bond just moves over here onto this side. So I'll show that as well. Now this double bond that doesn't actually move anywhere. It's still the same. And so we're not going to touch that. And the last part is that this double bond holding the oxygen moves up and forms a lone pair. We form a lone pair. And so we're going to show that as well. And these are all our arrows to show A into B. And I like to stress the fact that in our original we had a formal charge of 0. And in our final, even though we have two separate charges, they add up to a net charge of 0. In the next problem, we're trying to draw the Lewis structure of the nitrite ion. This is a question that we had in one of our earlier worksheets and in this unit. There's probably some confusion about how to draw nitrite. It's a little weird, but now it should make sense. And so after drawing this nitrite ion, we're trying to indicate some resonance contributors. So in other words, draw some resonance structures. And they want us to draw all the non-bonding pairs of electrons and indicate formal charges. We're just going to indicate formal charges where they exist. I'll verbally explain that we have no formal charge in a specific atom. Now the first thing I want to do is I realize this nitrogen is going to be my central atom because there's only one of them. And then our oxygen is going to surround this nitrogen. And it doesn't really matter which direction you show it. I'll just show it drawn this way. Now I know that nitrogen wants 3 bonds, and so well, the only way to really do that is to give this oxygen 1 bond and this oxygen another bond. And since I know our total charge in this nitride ion is negative, well, that makes perfect sense because this oxygen is going to have an extra lone pair, giving it a negative formal charge. This oxygen is happy, 0 formal charge, and this nitrogen still has a lone pair, meaning that it is also happy. But the question is, why did I decide to give this oxygen a single bond and this oxygen a double bond? Am I wrong by doing it the other way around? No, I'd be just as correct. The issue is that it would be a resonance structure. And so to draw a resonance contributor, we can actually kind of draw this reversed, right? We can switch our double bond. And so the double bond is now going to be on the upper oxygen, and the single bond is now going to be on the lower oxygen. But everything else stays the same. And these are both equally correct. Not one is not more correct than the other. And we're kind of incorrect showing both of these at the same time, right? They don't individually exist. They both exist at the same exact time. It's kind of like superposition. It's a little bit of a confusing fact. Now maybe a little extra that the question didn't ask us. Let's try to draw the arrows that show the resonance structure from this one to the right one. And so what's going to happen is that this lone pair is going to move down to form a double bond, while one of these double bonds is going to pop back up and form a lone pair. And so for the rest of this worksheet, I really like for you to think of resonance the way I do. Every resonance structure is kind of a step-by-step thing. Don't think of it as one entire movement across the molecule. Divide it into steps, okay? It'll help you move the arrows and kind of draw as many resonance structures as possible. We're not kind of mushing them all into one resonance structure. And this will make more sense a little bit later. The next question is a similar concept, except we're drawing nitroethane. And why do I think it's a similar concept? Well, it's literally kind of the same substituent, right? We have the N, and then we're going to have this group. Okay? So we're going to have a negative charged oxygen, a lone pair over here. Now the interesting here is that our total nitroethane does not have a formal charge. There's a net charge of 0. How does it happen? Well, this nitrogen actually has 4 bonds. It has no lone pair, which means that we'll have a positive formal charge on this nitrogen, meaning that, we have a positive and a negative, it equals out to 0. But why did I decide to give this bottom oxygen a double bond and not this upper oxygen a double bond? Am I wrong? No, I'd be just as right by showing the opposite, right? What if I were to give this oxygen a double bond, giving that lone pair, and the bottom oxygen, that single bond, meaning it'll have a formal charge of -1, and the nitrogen still has a formal charge of +1. Now, I doubt you guys are going to remember the nitro group. This is a nitro group, but it becomes super, super important in Orgo 2. And so if you want to start or keep it in the back of your head, these resonance structures are going to explain kind of the properties of why this NO2 acts the way it does. It's kind of special. It's pretty cool. All right, in the next couple of problems, we have to try to draw as many resonance structures as possible. And so what we're going to do is I'm going to use my strategy of kind of trying to move one thing at a time, not moving more than that. And I'm also going to use the strategies that I mentioned in the video, and if you're not familiar with these, go check out that video. I mentioned a really good hint for drawing resonance structures is that something positive on your molecule is probably going to attract some electrons, right? Either a double bond or a lone pair. There's probably going to be net movement toward that positive center. While lone pairs or a negative formal charge probably mean things are going to move away from it, right? Some double bonds are going to form away from it, or we're just going to move stuff in general away. Now, the first thing I notice in my first molecule is that I have a positively charged carbon at this end. Let's think about this. What does this mean? Well, this means that this carbon has 3 bonds, right? So it has 2 extra hydrogens, but it doesn't have a lone pair, which means that it could possibly accept another bond or a lone pair, right? That's absolutely doable. Well, we have a double bond adjacent to that carbon. So what's keeping us from actually just moving this double bond over here? This carbon can totally accept an extra bond. And so, again, moving one thing at a time, one possible resonance structure is the fact that I now have a double bond on this end. I still have my old double bond. Remember, net charges stay the same. Did we make a new positive charge? We absolutely did we created a positive charge right over here. Okay? Now, this isn't the end. We can still move this charge. Again, we're not going to try to move this one. We just did. That would get us our original. Let's try to make a completely new resonance structure. Now, this carbon has one extra hydrogen, right? So it has 3 bonds and no lone pair, meaning that it can totally accept another bond. So what's keeping us from moving this double bond away onto this carbon? And so what's going to happen is that we now get our new structure with our double bond over here, a double bond from the original movement, and now we have our formal charge at this carbon. Okay? And now, I doubt, again, you guys are going to remember this molecule, but this is also really important for Orgo 2. This is a specific type of diene. It's called a diene. It's kind of a flashback into the, not flashback, but look into the future. Don't have to remember it. Just a little interesting tidbit. Now, in the next structure, what I notice is, well, I don't have any positives and I don't have any negatives. Will my trick work? Absolutely it'll work. If you know anything about me, my tricks always work. And so what I'll notice is that, well, we have a lone pair on this oxygen, right? And so using my trick, a lone pairs or a formal charge of negative will probably mean that things move away from it. And so we're probably going to see a net movement of things either this direction or this direction. Now, why can't I move in this direction? Well, this carbon has 3 hydrogens, right? And it has no lone pair. I mean, it obviously can't have any more lone pairs, and it can't accept another bond. And so I most likely, well, not most likely, I definitely will not be moving anything to form lone bonds onto this carbon. And so this side is pretty much, undoable. We can't really move that. What we see in the left side, though, is we have a double bond, which means we can definitely move stuff. We have 2 carbons, 2 hydrogens on this ending carbon. And so what's keeping us from really just moving this double bond and creating a lone pair on the end? It's very doable, right? We can totally do that. I'm going to remove this arrow from the top. It's kind of bothering me. And so what we're going to do is we're going to draw our original molecule. Nothing happened to the lone pairs. But now we have a lone pair on the end of this molecule, on this carbon. What this means is we now have a negative charge. All right, we now have a negative charge. But over on here, since we removed one of the double bonds, we now have a positive charge. How is that understandable? Well, originally we had a net charge of 0. And we need to make sure that our resonance contributor also has a net charge of 0. And this makes sense. But this isn't it. We can still move something else. Remember, we have a lone pair on oxygen. And so we can totally move one of these lone pairs down and form a double bond. We can form a double bond. And so our oxygen is still going to be there. This lone pair doesn't move. We still have a negative charge over here. But now we have a double bond in this oxygen. One of the lone pairs still remains, except now this oxygen will have a positive formal charge. Positive formal charge. And still our net charge is still 0. And so this totally will make sense. Now in the next problem, we see that I have a double bonded oxygen, and I have some double bonds, maybe alternating off of it. This is going to become a really big theme in resonance structures. Double bonds or sources of electrons kind of alternating. And another big theme that you really have to keep in mind is a double bonded oxygen. You're going to see these a lot while you're practicing resonance. Why? Because this is a really popular form of resonance. One of these double bonds is always able to move up and form a new lone pair. You'll always see this, and you can kind of keep this in your mind. Once you see a double bonded oxygen, remember that you can move one of the double bonds up and form a lone pair. And so one of our structures will be a single bonded oxygen with an extra lone pair. Now what this means is that this oxygen is now going to have a negative formal charge, while this carbon, right in the bottom, the source of that oxygen, is now going to have a positive formal charge. Now what this means is that this double bond can totally move and form a double bond on the adjacent carbon. It can flip over onto this side. Why? Because this carbon is missing a bond. It can totally accept a new one. And so what we're going to have is a new resulting structure in which our oxygen still remains negatively charged. That dot did not look good. There we go. All right. And now a new double bond formed here and a positive formal charge on the ending carbon because we just lost a bond that it used to have. And notice that again, our net charge remains 0 in every molecule. Now in the next structure, we have a positive formal charge over here on this carbon, meaning, according to my trick, things are probably going to move toward it. Now I see this this double bond right next to it, which means we can totally move this double bond and flip it over onto the next carbon. Because this carbon, right over here, this positively charged carbon, can totally accept a new bond. So we're going to redraw this with nitrogen, hydrogen, hydrogen, a lone pair over here, and a new double bond. But what that means is that this old carbon, the carbon that now lost its bond, will now have a positive formal charge. But that's not it. Notice that I have a lone pair on this nitrogen. There is nothing keeping me away from taking off this lone pair and forming a double bond. And so what's going to happen is we now form our final resonance contributor, where we have nitrogen connected by a double bond, our old double bond. And notice, well, I originally had a positive charge. Where did the positive charge go? Well, now nitrogen has 4 bonds, which means it has one extra than what it likes, and it has a positive formal charge. By the way, if you're unfamiliar with what I just said, what it likes, and how I calculate these formal charges super quick, go back to one of my videos on the Lewis structures and formal charges video, and I have a really good trick onto how to calculate formal charges like a snap of a finger. I almost do it without even thinking, and that'll help you guys out. Now in the next problem, I notice that I have a negatively charged carbon, which means, if you guys remember, that a negatively charged carbon means it has 3 bonds and an extra lone pair. And so I'll draw that lone pair for us, just to show it. Now again, what I realize is that I also have a double bonded oxygen. And from 2 problems ago, what do you remember about double bonded oxygens? They're usually a source of resonance. And so I really like to begin my resonance with oxygen. We're going to move one of these double bonds up, form a lone pair. And what we're going to get is this resulting structure with a negative formal charge. But remember, our net charge has to be still minus overall. So we're still going to have this lone pair over here, negative charge here. And now the source of this carbon, the carbon holding this oxygen, is going to become positively charged. And since this has a negative charge, we have a positive charge over here, there is absolutely nothing keeping us from moving this lone pair down and forming a double bond. So what's going to happen is that we now have this resonance structure where this oxygen is negatively charged, and we have a double bond over here. And so overall, our net charge is still -1, while in the original, we also had -1, so our resonance structures totally make sense. The next problem is similar. We again have a negatively charged carbon, which means it should have a lone pair, and again, a double bonded oxygen. And so what this means is we can move this double bond up to form a lone pair. We're going to have a single bonded oxygen now with an extra lone pair, meaning it has a negative charge. Our carbon holding this oxygen will now be positively charged. We still have this lone pair here. Nothing happened to it. And so there's absolutely nothing wrong with taking this lone pair and moving it down to form a double bond. So what we're going to get is something like this. So we're going to have a double bond here, an overall negative charge, just like we did in the original problem. And the next 2 problems were just solely working with lone pairs. Now, the thing I notice is that I have a double bonded oxygen, so my rule of thumb, just start with that. We're going to move this double bond up, form a lone pair. What we're going to get is everything stays the same, except this oxygen is now a single bonded with an extra lone pair, negative charged, and the carbon that used to have that lone pair, that double bond, will now be positively charged. Now, what I also notice is that this oxygen has an extra, a lone pair that we can move, and so we can take this lone pair and bump it up into a double bond. And so this oxygen is still single bonded with a lone pair and a negative formal charge, and we have a double bond forming over here. We still have 1 lone pair on this oxygen, and since it has 3 bonds, it is now positive formally charged, which means that every structure in our resonance problem had a net charge of 0. The next problem is eerily similar. We'll start with that double bonded oxygen, move that double bond up, form an extra lone pair. Form an extra lone pair. So now we have a negatively charged oxygen and a positively charged carbon. And what this means is we can now take this nitrogen and move it down to form another double bond, similar to the previous problem. Which means that our nitrogen now has an extra bond. It now has 4 bonds. It has one more than what it likes, which means it has a positive formal charge, meaning that every structure over here had a net charge of 0. That makes perfect sense. Now in the next problem, we're moving away kind of creating resonance structures, and we're moving toward analyzing resonance structures. This is also an important skill. And now this is going to call for your realization of how things move. And so we're concerned with this original structure in the box, and we're trying to find which of these structures, 1 through 4, is not a valid resonance structure. Now the first thing I like to check is, well, my first rule of resonance. The first rule of resonance is that we only move electrons and we don't move atoms. And so I really like to originally, just right away, skim all my structures and make sure that we didn't add any atoms or move any atoms where they don't belong, right? Because we shouldn't be moving any atoms. And so what I notice is, well, number 4 has an extra hydrogen. Where did that come from? We can't add a hydrogen in resonance structures. And so we'll totally have 4 as an invalid resonance structure. This is totally invalid. And I'll circle this hydrogen for you guys to see. All right? And so we can kind of find the answer choices that has 4. Right, so now we're between C and D. I mean, we'll still consider the rest of them, but we know 2 of them is probably valid. Number 2 is probably valid because it's not on our answer choices. All right? And so what we're going to do is first, I'm going to try to see, well, is my net charge in my original molecule the same as the net charge in every other resonance contributor? And so this original molecule has a -1 net charge, and I can see that all my other molecules are also -1 total charge, which makes sense, right? That makes sense. We're not really going to be concerned with that. Now, all that's left for us to do is to really try to draw the resonance structures, right? And so this negatively charged carbon means that we have a lone pair, right? And for each of these resonance structures, we're going to try to see, well, where did this move? And what happened? And how can we do that? Is that possible? Well, for the first problem, we somehow moved this lone pair and formed a double bond. The issue with that is that our terminal carbon over here has 3 hydrogens. This carbon cannot accept another bond because over here, we still have this hydrogen. Remember, we don't move any atoms off, which means this carbon now has 5 bonds. That's definitely not valid. Carbon cannot have 5 bonds. And so I'm definitely thinking that this structure is our invalid structure. Now we're going to keep that in mind, but I still want to go through all the rest because, you know, practice is practice. Let's consider all the other structures and make sure that they make sense. In the next structure, we moved, well, this bond stayed the same, for sure. This bond appeared from where? Well, probably this lone pair moved up and formed a double bond over here. That's totally doable if we move this double bond. And we did, right? We moved this double bond and formed a lone pair in sulfur. And now sulfur, you have to remember, sulfur can accept a lot of bonds. It's kind of an exception to the octet rule. And so moving this double bond forms a lone pair onto sulfur, which wasn't there before, meaning that it should have a negative charge, which means this is totally good. This is totally correct. All right? Now in the next structure, let's reset. All right? In the next structure, somehow we got rid of this double bond and we formed a negative charge in the end of the carbon, which means we probably took off this double bond and formed a lone pair over here. Is that doable? Completely. We did that in the previous exercises, right? We can totally do that. But we also formed a double bond over here. And so how did that happen? Well, we took this lone pair and we formed a double bond. And now everything's happy. We didn't really break any octet rules, and we still kept a negative charge. And so this is totally valid. This is totally good. And so I'm thinking that my answer choices are structure 1 and structure 4. So D. In the next problem, we're considering which of the species is a resonance form of the original, which is in the box, kind of the opposite of the previous problem we were doing. So to find the valid one, let's first follow my checklist. Let's see if all of them don't break the first rule of resonance, which is just movement of electrons. Do any random atoms move or appear or disappear? Well, I don't really see anything. If I'm wrong, let me know in the description below or in the comments. but I don't see any protons or atoms moving or disappearing. And so I think all of them are mostly good in that aspect. But what about net charge? So our original molecule had a net charge of +1. And I'm looking at it, and all our other molecules are also have a net charge of +1. So we kind of can't cheat this answer choice. We kind of can't have a trick. We have to actually analyze. And so what we're going to do is let's try to form each of these resonance structures one by one. Let's figure out how we can do that and if they're valid. Okay. Well, our original structure had a positive formal charge on this carbon over here holding the phosphate, which means most likely, knowing the patterns that you should maybe already be aware of, is that probably something's going to move toward this carbon, right? But let's not, be carried away with that assumption. We can totally have something else going on in this molecule and not resolve this positive charge. Okay. Well, in the first structure, we got rid of that positive charge, but how? Like nothing moved toward the positive charge, right? So how did we get rid of that positive charge? And then we somehow formed a lone pair right over here, right? And so we formed another positive charge over here, but we got rid of the original one. How is that possible? It's not, right? It doesn't make sense. And so this first structure is totally invalid. Totally invalid. Not good. Our next structure is going to have a positive formal charge somehow on this carbon. How did that happen? Well, we're assuming that this double bond moved over here. We're not assuming. We can see that this double bond moved over here. But wouldn't that mean that the positive charge would form over here? How did we form the positive charge on the next carbon? That doesn't make sense at all. And so this is also invalid. Totally invalid. Doesn't make sense. How did we move that that positive charge? Doesn't make sense at all. In the next structure, what we can see is that, well, somehow we got rid of this positive charge, but we formed that positive charge in the phosphate. Well, now, if you know anything about phosphate, phosphate will have a lone pair over here. And so phosphate can totally form a double bond over here. But what that means is that phosphate will now have an extra bond, meaning that phosphate will now have that positive charge. And nothing else in the molecule moved. And so this is totally valid. Why not, right? This is totally a great way to, I guess, get rid of this positive charge on the carbon. All right, what I was thinking of is moving this double bond over here. But, that's why you don't go in with any preconceptions. And so this is totally good. I think this is good, but let's check the last structure just in case. In the last structure, what we realize is we'll probably move this double bond over here, which means we should form the positive charge over here, but we didn't. We somehow formed the positive charge all the way in the end, and the only way for that to happen is to remove a hydrogen. And we know that's not possible. We can't do that. Even more than that, we somehow made another double bond over here. How did we get a new double bond? Like, where did that come from? It doesn't really make sense. And this is totally invalid again. And so our answer choice is C. In the next problem, we're trying to find which one of these species is a valid resonance structure of the original in the box. And so let's follow my checklist. Let's make sure we didn't appear any atoms or things that we didn't belong. So I'm looking at all of these and I don't see anything, right? We kind of didn't get rid of anything very obvious. Maybe there's a hydrogen hiding in there somewhere, but it probably isn't, right? And so the next thing that on my checklist is let's make sure all of the net charges are -1. So our original is -1, which means that everything else should be -1. And I'm looking at it and it looks like all of them are -1. Excellent. And so our next obvious step is to really figure out which ones are valid or not. And so this negatively charged carbon means that we have a lone pair over here. All right. And so the first resonance structure, we kind of formed a new lone pair on this carbon. How is that possible? Well, what if we move this double bond over here and we form that lone pair? That's definitely doable. And we didn't do anything to the nitrogen and everything around it is still the same. But we formed this double bond over here as well. Well, that's totally possible if we get rid of this lone pair and form this double bond, right? That's totally doable. This is very valid. We're very good. I'm happy with this answer choice. All right, let's reset. The next answer choice, somehow we form a negative charge on this carbon. Now, realistically, that's not possible. We have a hydrogen over here. And to form a negative charge means that we have to remove this hydrogen and form a new lone pair. So that's definitely not possible. But more than that, we can't even move this double bond here because that means we'll be breaking the octet rule. And so this next structure definitely doesn't make sense at all. This is totally invalid. Invalid. All right, let's reset. Our next answer choice is kind of manipulating nitrogen. Now we notice that I kind of disappeared this double bond over here and formed a lone pair on nitrogen, negative charge, meaning that I probably took this double bond and formed a lone pair. And that's totally doable, right? That completely makes sense. And then another thing is that, well, we formed this double bond. And so what that means is after this step, we'd have a positive formal charge in this carbon, meaning that we can totally move this lone pair and form a new double bond on this carbon. Meaning that we'll now get rid of this charge and we'll be left with that negative charge in that nitrogen. This is totally valid. This totally makes sense. Let's reset for the last time. And in the last structure, we kind of do the same thing, right? We form a negative charge on nitrogen, and so we're going to move this double bond up and form a lone pair. But how do we form this double bond? How did that make sense? Where did it come from? I mean, this double bond makes sense, right? We can kind of get rid of this lone pair and form the double bond. But where did this one come from? It doesn't really make sense. It came from nowhere, right? And so this is totally invalid. This doesn't make sense. And so our answer choice is going to be B. Structures 1 and 3 are going to be valid structures. All right, in the next problem, what we have to do is try to find which one of these options is not a valid resonance form of the original structure that we're given. And so, like always, let's start by, putting our lone pairs on our oxygen is probably going to be useful. And so let's look to make sure that none of these options have any atoms or any changes in any atoms. And looking at them, I don't see any changes. The other thing I want to check is that our net charge is +1, because our original charge was +1, so all of our structures must have a net charge of +1, which they all do. And so let's go one by one and try to figure out what bonds moved and make sure that the structure works. So the first structure, kind of move the double bond over onto the right. But for some reason, our formal charge should appear up here, right? Because we just lost that bond. But they draw it down here. Well, that doesn't quite make sense. So I'm kind of thinking of A as an invalid resonance structure, but I'm not quite sure yet, so let's just make sure. Our structure B is actually exactly what we just drew. We're going to move this double bond over, and we should form that positive formal charge over on that carbon on top. And so this is completely valid, all right? That works. What we can do with the next structure is, well, what if we were, instead of moving this bond, what if we were to move this terminal double bond over onto this carbon? Well, if this were to flip over, then we would form a positive formal charge on the end carbon, on the terminal carbon. And that makes sense, right? This is completely valid. That makes complete sense. Answer choice D is kind of a development of B, it looks like. What we end up doing is, well, let's reset here for a bit, is if we were to flop this double bond down, we would form a positive charge here, but we can actually kind of just break this double bond down and form break one of those lone pairs and move it into a double bond. And that would form a positive charge in that oxygen, right? And that should work. This is completely valid. And our answer choice E is actually, looks like the same choice as B, right? This looks like the same thing, interestingly enough. And so this is definitely also valid. And so A is our invalid choice. The next question is asking us to find the valid resonance forms of the species in the box. And so first, as always, let's make sure that none of our atoms were moved, which none of them are. Let's make sure that all of our structures have a net charge of -1, which actually 3 does not have a net charge of -1, which means that structure 3 is invalid. So let's just eliminate all the choices that include 3. Okay, and so let's start by analyzing our resonance structures. We can say that we have a lone pair here on this carbon since it has a negative formal charge. And so if we were to look at structure 1, somehow we don't touch anything else, but this lone pair comes off and forms a double bond right over here. But for some reason, we form a negative charge on the ending carbon. We actually wouldn't even be able to move this double bond over because this carbon has 4 bonds already, right? And if we were to give it another bond, we would be breaking that octet rule. And so number 1 is also completely invalid. All right. If we were to reset, let's redraw that lone pair. Well, in structure 2, what we're doing is we're probably moving one of these double bonds up, right, to form that extra lone pair, which is giving it that negative charge. And then we're moving this lone pair and forming that double bond over here and not touching anything else. And that makes perfect sense, right? That's good. That makes sense. That works. In structure 4, let's redraw that lone pair. What we're doing is that somehow we don't touch any of these bonds, but somehow we give it another lone pair and it becomes a negatively charged oxygen. That doesn't really make sense. I don't really understand how that happens. And plus, look at this carbon right over here. It looks like it has 5 bonds, which breaks the octet rule. And so this option is also invalid. And so I can say that 1, 3, and 4 are invalid, and only 2 is the correct resonance structure. In the next problem, we're trying to find out which structures are not valid resonance structures of our original in the box. And so what we can do is we can try to figure out which ones, well, do we add any atoms as usual? Well, looks like everything is mostly the same. Is our net charge the same? So our net charge over here is 0. So our net charge on any molecule should be 0, right? This, many charges going on, but it still equals to 0. This one does not equal to 0, right? Definitely does not equal to 0. And so we definitely know that number 3 is invalid, but according to the answer choices, we could have an extra one. And so let's not cross this out. Let's actually circle this since it's an option. Okay, and number 3 also has a net charge of 0. So let's start analyzing each answer choice. Interesting example. This little group here is that nitro group that we had earlier in the worksheet. And so you guys should be familiar with this resonance, is that we can move one of these bonds up to form that lone pair. And then one of the extra lone pairs in this oxygen can move down to form that double bond next to the nitrogen. The nitrogen's charge doesn't change at all. And so this is completely good. This is a valid structure. Now what can also happen is, what if we were to pop this double bond up, form that extra lone pair, and instead move one of these bonds down, right? Since we move that double bond down, we still have 4 bonds in that nitrogen, meaning it has a positive charge. And if we were to stop there, we would have a positive formal charge on this carbon. But answer choice 2 doesn't stop there. We can actually continue, move one of these double bonds down, and then what that would form is a formal charge on this carbon. And we still don't stop there. Remember that chlorine, all halogens actually have lone pairs available. And so we could take one of these lone pairs and form a double bond, right? Creating a positive charge in that chlorine. You don't see that much with halogens, but it's possible, right? What's telling us that that's not possible? It's completely valid. The last answer choice, we again kind of pop this double bond off, form a lone pair. One of these double bonds will move on to the nitrogen, leaving that positive charge in that nitrogen. And then again, we kind of move one of these down into this bond, and then we leave that formal charge here. So answer choice 4 is just like answer choice 2, but not going all the way. And so answer choice 3 is our only invalid resonance structure. The next problem, we're trying to figure out which of these structures is not a valid resonance form of the original that's in the box. Again, let's try to find the ones that are completely invalid. The first one looks kind of weird. We're actually just flipping this molecule, but nothing's telling us that we can't do that, right? That's fine. And the rest, we're not really making anything new, right? We're not adding any carbon atoms. And it looks like all of our structures have a net charge of -1, which makes sense. And so in the first structure, what we can do is we can actually form, first of all, show that we have a lone pair on this carbon. And what we can do is to form this structure is, if you look at it, kind of imagine it, well, this is kind of this side, is that none of these bonds actually move except for this lone pair. And so this lone pair will form a bond over here. And instead, this bond will pop off and form a lone pair on this terminal carbon. And that's what will form this lone pair, this negative charge on this ending carbon in the middle. And so that makes sense. This is completely valid. In the next answer choice, it looks like we're not moving any of these bonds. Instead, we're just moving one of these lone pairs up. And then somehow we are supposed to, I don't know, create a lone pair on this carbon, right over here. and then somehow that would get rid of this bond as well. Like, I'm not exactly sure how that works. That doesn't really make sense. And so I think this structure 2, is invalid. That wouldn't really make sense. These bonds are coming out of nowhere. The next structure, what we're doing is that we're keeping this bond. We're forming a negative charge on this carbon, so that means that we're probably popping off this bond and forming a lone pair. And then this bond forms, which means that we create this bond from this lone pair, and then everything else stays the same. And so that completely makes sense, right? That's fine. So 3 is a completely valid structure. In the next problem, what we're doing is we're keeping these 2 bonds the same, this ending bond the same. We're probably forming a lone pair through here, and then this lone pair comes off and forms a bond here. And so we end up with a lone pair here, which means a formal charge of -1 on this carbon. And that makes sense. That's completely valid. And so our only invalid structure is structure 2, which is answer choice B. The next structure, we're again looking for species that are not resonance forms of the original in the box. And so let's check that all our atoms are the same. It looks like it is. Let's check that all our structures have a formal charge of +1, which all of them do. And so let's remember that, well, we have a formal charge of +1 on this carbon, which means that we can probably accept another bond over here. And that's most likely what's going to happen. And so the first structure, somehow we remove this double bond and move it over here. The problem with that is that this ending carbon, this terminal carbon, already has 3 hydrogens, which means it can't accept another bond. And then somehow we're getting rid of this formal charge as well. That doesn't really make sense. I think this is an invalid structure. And so, again, I keep crossing this out, but it's actually an answer choice, so we should probably circle it. In the next problem, we are moving this bond over here, which, completely doable, and that would form a positive charge over here, which totally makes sense. This is completely valid. This is a good resonance structure. The next answer choice, we're plopping this bond over onto the next one, which means this didn't make sense, right? Because this carbon can accept another bond, and then this carbon would become that positive formal charge, which makes sense. This is completely valid. And then the next answer choice is kind of a development from there. After we form this formal charge of +1, one of these lone pairs from the sulfur can actually come down and form that bond to relieve that formal charge. And instead, the sulfur is going to pick up that formal charge. And so this is also completely valid. And so I think answer choice 1 is going to be the only invalid structure. In the next problem, we're again looking for the structure that is not a valid resonance form of the original in the box. Let's make sure that none of the atoms are moved, which none of them look like they are. And all of these structures have a formal charge of +1, which makes sense, right? That's cool. In the first structure, we are somehow creating a bond over here, which makes sense, right? We can take this lone pair and move it up to form that bond, which gets rid of this formal charge but creates a formal charge of the nitrogen. And we're not moving anything else, which makes sense. This is completely valid. In the next structure, what we're doing is we're probably going to move this bond down and form this lone pair. Form this formal charge of +1,